right? In the miscellaneous, there's a proof of the limit as x approaches 0 sine x over x. It's kind of neat. Use the geometry. I do think it's interesting that, oof, what you're really saying with this is that as theta gets really, 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 really small, the sine of theta and the angle theta approach the same value essentially, right? Because their quotient is equal to one. Kind of neat, kind of. That said, there's a lot of things we do with this. So we use this fact, and I would say more generally, the way you want to think about this is that if you have the limit as some stuff approaches zero of sine of that stuff divided by the exact same stuff, it has to be the same, that limit is one. So if someone wrote something like the limit as x approaches 4 of sine of x squared minus 16 over x squared minus 16, well, the two requirements are met. The stuff is the same. It's sine of some stuff divided by the same stuff. And importantly, the stuff is getting closer and closer to zero because as x approaches 4, x squared minus 16 is getting closer and closer to zero. So this limit would also be 1. And there's not really any work to show here. I should say, without L'Hopital's rule in play, which it's definitely not until the end of the quarter, there's not really any work you can show here. The only work you really can do is try to make it look like you have sine of a thing divided by the same thing, and that thing has to be getting closer and closer to what? Right, to zero. So it's all well and good when things are written and things are the same. Like if you have the limit as theta goes to zero of sine of 5 theta over 5 theta, we're happy about that because the stuff is getting closer to zero and it's the same stuff in the sine function that we're dividing by. That limit is also 1. No work to show. On the other hand, I can use this other side of the paper here. If you start having things where you have maybe sine of 2 theta over 6 theta, we're close, but we're not quite there, right? 2 theta is getting closer to zero. 6 theta is also getting closer to zero, but they're clearly not the same. So what do we do? Well, there's a number of ways to do this. I'll show you what I think is easiest. When I do this, I like to rewrite it like this. The limit as theta goes to zero of sine of 2 theta over blank times blank over 6 theta. So all the pieces are still the same, right? I haven't actually changed anything. I've just written in this really awkward way. And then I like to ask myself the question, or ask you the question, what do we wish was beneath sine of 2 theta? 2 theta, right? We want because the thing inside the sine function you can't change really. It's stuck being what it is. But you can definitely multiply or divide by anything you want to. So if we divide by 2 theta, we also have to multiply by 2 theta. But then this works out really nicely. 2 theta divided by 6 theta, the thetas cancel. 2 over 6 is just 1/3. And if you really want to be very specific about your work, you can bring that 1/3 constant out in front of your limit and say it's 1/3 times the limit as theta approaches zero of sine of 2 theta divided by 2 theta. And that's going to be 1/3 times 1, which is 1/3. The more typical thing to do is just to say this equals 1 times 1/3 and be done with it. Like I'm kind of doing a little more work than I really need to here. In a similar way, I would like all of you to, well, first, I'm going to write this limit, sine of 7 theta over 5 theta. In your heads, make a good guess as to what you think the answer is going to be. I bet you all have a pretty good guess based on what the previous one was. Now do it. Do the work I just did in a similar way. Use what I call this the wish method because you wish for what you want either above or below the sine function. So try that for a minute. That's almost a minute. So here, same sort of deal. And again, this is not the only way to do this, right? This is just how I think is easy, but I can show you another way in a minute. I would rewrite this as the limit as theta goes to zero of sine of 7 theta times something over 5 theta, and then I want a 7 theta here, and I have to have a 7 theta there to make sure I've only multiplied by 1. And then the thetas cancel, or divide to 1. The limit of this part is going to equal 1, so I'm going to get... Now, I should be careful here. I'm being a little bit disingenuous with what I've written. Sine of 7 theta divided by 7 theta is not equal to 1. The limit as theta approaches 0 of sine of 7 theta over 7 theta is equal to 1. Not the same thing, right? The limit is what gives us the actual value here. So later on, when we start talking about derivatives and we're going to get to some place where we have like a sine x over x, remember that that's not equal to 1. I'll definitely remind you that it's not 1, but some people will be like, can't we just replace that with 1? No, it's not. There's not a limit there. So because we have a limit, you can say, okay, this part's going to go to 1. That's 7/5, so you get 1 times 7/5, which is 7/5. Other people might approach something like this and say, I would rather do it like the limit as theta goes to 0 of sine of 7 theta over 5 theta, and then just multiply the top and bottom by 7/5. That totally works too. To me, I feel like you have to think harder for that one. And then on top, you get the limit as theta goes to 0 of 7/5 times, well, let's bring the 7/5 out in front, times sine of 7 theta on top. And the bottom, 7/5 times 5 theta is 7 theta. So you see, we get to the same place. Still going to be 7/5. Cool. They do get more complicated with the sine, cosine, or no, erase cosine from your mind with these sine kind of things. But really, when you see a 0 over 0 type like this, because again, what I really should have started with is these are all 0 over 0 types of limits, right? If you plug in theta approaching 0, or in this third one, x approaching 4, you're getting sine of 0, which is 0, over 0, which is 0. And the 0 over 0 is anything. So the things to look out for, I would say, are essentially signs showing up in your limit. So someone could try to hide it. They could write something like the limit as x approaches 0 of 5x over cotangent. Sure, cotangent. Yeah, no, what do I want here? I forgot what I was going to do. Cotangent is not what is that what it really? Sorry. I guess, sorry, that's not what I wanted at all. I wanted 5x times cotangent. Apologies. Limit as x approaches 0 of 5x times cotangent of x. It's a little harder to see that this is a 0 over 0 type. In fact, if you plug in 0, you get 0 times, well, cotangent of 0 is undefined. I don't love to leave it like this. I personally would almost always choose to rewrite when it's limits, would choose to rewrite trig functions in terms of sine and cosine. Meaning cotangent is going to become cosine over sine, tangent is going to get rewritten as sine over cosine, cosecant is 1 over sine, secant is 1 over cosine, which probably won't show up as much. So here, I'm going to reimagine this or rewrite it as the limit as x approaches 0 of 5x times cosine x over sine of x. If you like, you can think of this as 5x over 1. You don't really need to. But then your job really is to kind of group the x and the sine x together and everything else off on its own. So here, we would write this as the limit as x approaches 0. I want the x with the sine x. So I have x over sine of x. And then the leftovers are 5 times cosine over 1, although you don't really need the 1. That's how I'm choosing to rewrite this. Now, you might say, well, James, that's not quite what you said before. Before it was sine x over x. Well, here's the good news. X over sine x, it acts the same way. And what we really said before was as the stuff gets closer and closer to 0, x and sine of x, or theta and sine of theta, are both getting closer to each other. So their fraction, whether it's sine x over x or x over sine x, should be getting closer and closer to 1. If you don't love that, that's fine. Here's another way to think about it. I'm going to rewrite x over sine of x as, kind of annoyingly, 1 over sine x over x. Still times 5 cosine of x. I don't really need these parentheses here, but I just decided to write them in. So, okay, that's a little small. I could write bigger. I could really try to write bigger. I will try. Um, and now, so we should do this, yeah. So technically, when we take this limit, we kind of just do it all at once. Like we say, okay, the limit of the sine x over x is 1, and the limit of the 5 cosine x is 5 times cosine of 0, which is 5. We're really using some of the limit rules. We're just kind of not saying we're using them. So here's what we're actually doing without saying we're doing it. We're going to use the product rule and say it's the limit as x approaches 0 of 1 over sine x over x times the limit as x approaches 0 of 5 cosine of x. And then we're going to use the quotient rule for this first one, meaning the limit of a fraction is, don't write all this out, by the way, unless you really, really want to. But the limit of this fraction is the limit of the top over the limit of the bottom. And the limit of 5 cosine x, well, constant multiples get to come out in front, so this is really 5 times the limit as x approaches 0 of cosine of x. And then the limit as x approaches 0 of 1 is 1. The limit as x approaches 0 of sine x over x is also 1, because we already know that. The 5 hangs out, and the limit as x approaches 0 of cosine of x, well, we can plug in the 0 and get cosine of 0, which is 1. So we get 1 times 5 times 1, which is 5. And no one should ever write that work out. But the point is we are using all these limit rules that you've talked about in class to just say we can kind of plug in 0 and get the thing we're getting. Let me show you one more example of this because it is kind of worthwhile to be aware of these limit rules. And not just kind of, it is important to be aware of these limit rules. So let's look at, sure, the limit as x approaches 2 of 3x squared plus 5x minus 7 over 2x cubed plus 9. Now, the way you should actually do a limit like this is plug in 2 for each x and see if you get a number that's not 0 over 0, because 0 over 0 is not a number. And you will. But if you actually plug in 2, you're going to get 3 times 2 squared plus 5 times 2 minus 7 over 2 times 2 cubed plus 9, which is something, right? It's 3 times 12 plus 10 is 22 minus 7 is 15 over 8 times 2 is 16 plus 9 is 25. And then you can reduce that fraction to 3 over 5. But what we are all actually doing when we do that is using all of the limit rules that says, for example, that the limit of a fraction is equal to the fraction of the limits. Its limit as x approaches 2 of the top divided by the limit as x approaches 2 of the bottom. Now, there's something I'm not saying here, which is kind of important. You're only allowed to do this if both of these limits exist. Right? You can't break it up so that something that existed before is broken up into a piece that doesn't exist and does exist. Right? So I'll show you. Let me step aside from saying that for a second. We'll talk about an example with that in a moment, so you kind of see like what I mean. But for now, it's okay to do it as long as it works, which I know sounds kind of stupid, but that's really how it works. It's okay to do what we're doing as long as it doesn't result in something erroneous. Now we're going to use another limit rule. That the limit of a sum is the sum of the limits. So the limit of this plus this minus that is really the limit of this plus the limit of this minus the limit of that. So and this is where it gets annoying to write out. It's going to be the limit as x approaches 2 of 3x squared plus the limit as x approaches 2 of 5x minus the limit as x approaches 2 of 7 divided by, same deal on the bottom, the limit as x approaches 2 of 2x cubed plus the limit as x approaches 2 of 9. Okay, in the next step, we're going to apply a few different rules. For the 3x squared, the 5x, and the 2x cubed, we're going to apply what's called the constant multiple rule, which is that if you have the limit of a constant times a function, that constant gets to come out in front. Or in other words, the limit as x approaches 2 of 3x squared is the same as 3 times the limit as x approaches 2 of x squared. Same deal here. The limit as x approaches 2 of 5x is 5 times the limit as x approaches 2 of x. And, whoops, that's an x. And the limit as x approaches anything of a constant is always that constant value, right? If the function is just 7 the whole time, it doesn't matter what x is getting close to. You're still going to get 7 at the end of the day. So that's just 7. Similar process on the bottom. The limit as x approaches 2 of 2x cubed is 2 times the limit as x approaches 2 of x cubed. And the limit as x approaches 2 of 9 is just 9. We're almost done. Thank goodness. Finally, the limit as x approaches 2 of x to a power is just the number it's approaching to that power. So we get 3 times 2 squared plus 5 times, as x approaches 2, x is getting closer to 2. Minus 7 over, as x approaches 2, x cubed gets closer to 2 cubed. So 2 times 2 cubed plus 9. And it's exactly the same as up there. So we end up still getting 15 over 25, which reduces to 3 over 5. So why did we do all that? So that we recognize that when we're doing this thing where we just plug in whenever x is approaching, there's really all of this machinery that's building it up for us. And it's okay to skip it all, but we do need to be aware that it's in play. Because later on, we will use some of these rules explicitly because it's useful to kind of see what's happening. Like when we talk about finding the derivative of sine of x or of cosine of x, there's an important place where we kind of use the fact that the limit of a product is the product of the limits. So just want to make that clear. Trying to think about an example that's it's hard to come up with an example where things don't work out nicely because most of our examples work out nicely. What was I trying to think of here? Ugh, apologies. I thought I had an example in mind, and now I'm like, do I have an example in mind? Oh, maybe that one. Maybe that one. Sorry. I'm like racking my brain here. Like, can I think of something where Sure, I guess this is fine, although it's kind of weird. So, for example, the limit as x approaches, what do I like for this? Sure, this is gonna seem kind of dumb, but bear with me. As x approaches 0 of, sorry, this like, do I like that? Sure, fine. X times sine of 1 over x, which I think we talked about last class. You can't break this up. So here, even though this limit does exist, we'll show it again with the squeeze. I'm just gonna think it's a good thing to see again. You cannot say that the limit of this product, this is not equal to the product of the limits. Specifically because one of these limits on their own doesn't exist. The limit is x goes to 0 sine of 1 over x. This limit does not exist. In fact, you can see that graphically. I know we talked about last time. I know I'm showing you again, but I think it is worth seeing one more time. So just as a reminder, if you look at sine of 1 over x, it looks super funky. As you get closer and closer to 0, sine of 1 over x oscillates an infinite number of times. It just goes up, down, right? It just looks right. There's no getting close to any particular number here. So to be able to break up a limit of a product as the product of limits, both the limits have to exist on their own. You can't do it if they don't. So that's what I meant when I said these rules have some minor restrictions. Cool. Okay. So one more of these sine cosine ones. So just one more example here. These sine cosine things, I keep saying cosine like is these sine limits, really not with cosine, where you have like a 0 over 0 type, they're usually best dealt with in the way we've been dealing with them. For example, if someone gives you like the limit x approaches 0 of sine cubed of 5x over 2x cubed, later on we'll see that you can do this a different way. And later on we'll see that you should not do this a different way because it's really, really gross if you try to do this some other way than what we're about to do. Like if you try doing L'Hopital's rule on this thing later on, you're going to be real sad about it because it's ugly. Maybe not the first time and the second time, but you have to do L'Hopital's rule like 3 times on this one, and it's gross. Here, we should definitely use our other tools that we have. That I'm going to write sine cubed of 5x as sine of 5x times sine of 5x times sine of 5x times something over 2x cubed. If you really wanted to, if you don't like having these extra x's, you could say each of those x, each of the x's in x cubed, you put one here, and one here if you prefer to put them there. That totally works too. I'm just going to fill in a 5x here and a 5x there, a 5x here and a 5x there, and a 5x here and a 5x there. And instead of showing all the little limit rules that we just talked about, we're just going to say this limit is equal to, well, the limit as x goes to 0 of sine of 5x over 5x is 1. And the limit of that is also 1. And the limit of that is also 1. And this thing here simplifies to 5 times 5 times 5 over 2. Because the x cubeds cancel out. And we end up with 125 over 2. Or 62.5. Not that you should change it to that, but, well, yeah. That number shows up later on, sometimes in 21C. No, 21B, because it's like the weight density of water. It's like water weighs like 62.5 pounds per cubic foot or something like that. So that's why, that's the only reason I did that division there is because like this number you'll see later on. It's kind of neat. Cool. So is that all I wanted to say about that? Let's see here. Sure. Right. Okay. That seems good. Yeah. So last time we had started at the end of class, we had started talking about limits as x approaches infinity. And I had done like one example and we kind of seen that, oh yeah, we want to divide by the highest power of x. So let's do a couple more of those because I want to just make sure everyone's on the same page about all of that. So let's look at the following limit. The limit as x approaches infinity, that's an infinity of, let's make this not terrible. Let's make it, sure, real easy. 2x plus 5 over x plus 1. Now, I'll point out, if you quote unquote plug in infinity, we have an infinity divided by an infinity type. An infinity divided by infinity is also an indeterminate form. Indeterminate form. Similar to 0 over 0. And again, you should see this word and be like, yeah, indeterminate means we don't know what it is yet. Because usually indeterminate means we can figure it out. There's something to do and we're going to do it. Here, you could start plugging in numbers. In fact, if you start plugging in numbers, like if x is equal to 1,000, you're going to get your function value. Let's just call it y. Y is going to equal 2005 divided by 1001, which is probably pretty close to 2. Let's see here. 2005 divided, well, that's a decimal place. 2005 divided by 1001, 2.003 approximately. And if you go bigger, like if x is a thousand, if x is a million, y is going to be 2,000,005 divided by 1,000,001, which is probably even closer to 2. It's looking like the limit's going to be 2. Do I have enough zeros there? Let's see. 1, 2, 3, 4, 5. Not that you don't believe me, but I just like to see. Sure, it's 2.000003. So yes, we're getting closer and closer to 2. How can we actually do it? Well, I imagine you might know at this point that when you have a rational function, right, a polynomial divided by another polynomial, if the highest power of x on top and the highest power of x on the bottom are the same, then the limit's going to end up being the fraction of those leading coefficients, 2 over 1 in this case. One way you could see it is by actually doing the polynomial division, right? If you actually divide 2x plus 5 divided by x plus 1, let's see, x goes into 2x 2 times. 2 times x plus 1 is 2x plus 2. We subtract. 2x minus 2x is 0. 5 minus 2 is 3. We can rewrite 2x plus 5 over x plus 1 as being equal to the quotient 2 plus the remainder 3 that still has to get divided by x plus 1. And now it might be easier to justify yourself, oh yeah, if x is getting really, 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 really big, this part here is going to get really, really, really close to 0. That's not the only way to do it, but I do think it's nice to kind of remind yourselves of, oh yeah, there's this thing called polynomial division. In fact, definitely it's going to come up when you take 21B. You will be doing some, not a lot, but there are some problems where doing the integral of this certain thing is really only doable if you do the polynomial division first. So good thing to remember for next quarter. But really the technique typically is to divide everything by the highest power of x that is in the denominator. So here, if you're actually doing this one, and typically on your first exam, even if you know the shortcut is giving you an answer of 2, they still want to see the work for this kind of problem. So here, if I was finding the limit as x goes to infinity of 2x plus 5 over x minus 1, I would either divide the top and bottom by x or factor out an x, either way. I suppose let me be super clear about this. I got 2x plus 5 on top, divided by x, and x minus 1 on the bottom, divided by x. So that you can see I'm doing the same thing to the top and the bottom. So I'm really not changing it, right? I'm multiplying the top by 1 over x and the bottom by 1 over x. I'm really just multiplying by 1, which is totally allowed. We can always multiply by 1. But then we get the limit as x goes to infinity of 2x over x is 2, 5 over x is 5 over x over x is 1, 1 over x is what it is, and then as x gets really, really big, 5 divided by something big gets really small. 1 divided by something big gets really small. So we end up with 2 plus 0 over 1 minus 0, which is 2. So that's how you would show the work for a problem like this. In fact, why don't you all try showing the work for the next one? So find the limit as x approaches negative infinity of 3x to the fourth plus 5x squared minus 7 over 7x to the fourth plus 3x cubed minus 2x. And even though you probably already know what the answer is, practice showing the work. Divide everything by what? X to the fourth power. The highest power of x in the denominator. Yes, I know they're the same here, but it's going to matter in a minute. Do it. We should talk about that. Again, a reminder, we are doing the same thing to the top and the bottom of this fraction. We're multiplying the top by 1 over x to the fourth, we're multiplying the bottom by 1 over x to the fourth. Or you're dividing the top by x to the fourth, and you're dividing the bottom by x to the fourth. But as long as you're multiplying or dividing by the same thing in the top and the bottom, you're just multiplying by 1, which is legit. And then we simplify. We try not to write too many steps because, So we have 3 plus 5 over x squared minus 7 over x to the fourth over 7 plus 3 over x minus 2 over x cubed. And all these things divided by x to some power are getting really, 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 really large. It doesn't matter if they're negatively large or positively large. 5 divided by a really big number, whether it's positive or negative, is still getting closer and closer to 0. And so are all of these things. So unsurprisingly here, we end up with 3/7. I will point out whether or not x is approaching infinity or negative infinity, we still would have gotten the same result, right? Dividing by negative infinity squared is going to give you 0 just as well as dividing by positive infinity squared, or negative infinity or positive infinity here is still going to give you 0. Usually, I'll back that up. For rational functions, meaning a polynomial divided by a polynomial, the left-hand limit to infinity and the left-hand limit to negative infinity and the right-hand limit to infinity, if they exist, are always the same. You're always going to get the same value to the right as you get to the left for rational functions, meaning polynomials divided by polynomials. There are some other special functions that the limit to the right and the limit to the left aren't the same, or one of them is existing and one of them is not existing, which is going to translate to what kind of horizontal asymptote the function has. This function has a horizontal asymptote at y equals 3/7. So just as a point, we have a horizontal asymptote, y equals 3/7. Let's look at some other examples here. Sure, that's fine. Let's look at, I don't love that one. Let's do that one instead. Sure, sorry, 1 second. Sure, let's look at f of x equal to 2x minus 3 over x squared minus 2x plus 1. And I am interested in what's the limit as x goes to infinity of this thing. You might already know what happens. You might be able to say, hey, look, well, we're still getting infinity over infinity, but in this example, unlike the previous one, the denominator is growing much faster than the numerator because you have a higher power of x. And if your denominator is larger, your fraction is small. So we would expect this limit to be 0 because we have a much, much bigger denominator than numerator. That said, we're still going to show the work. So we're going to divide everything by the highest power of x in the denominator. So everything by x squared. So here we're going to get the limit as x approaches infinity. Let's just divide and do the simplification. So 2x divided by x squared is going to be 2 over x. 3 divided by x squared is 3 divided by x squared. X squared divided by x squared is 1. 2x divided by x squared reduces to 2 over x. And 1 over x squared is 1 over x squared. And then all the things divided by something getting big are going to go to 0. So that's going to go to 0. 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 And we end up with 0 minus 0 over 1 minus 0 plus 0. And 0 divided by not 0 is 0. Meaning this function has a horizontal asymptote at y equals 0. I will point out this function crosses its own horizontal asymptote because it definitely has an x-intercept at x equal to 3 over 2. Good to know. Functions can definitely cross their horizontal asymptotes. Lots of times. Actually, they can cross their horizontal asymptote an infinite number of times. You even know a function, sine x over x. That function crosses its own horizontal asymptote an infinite number of times. Kind of neat. Kind of. Not that neat. So when your degree on top is smaller than your degree on the bottom, the limit's always going to be 0. Because the denominator is getting bigger than the numerator, so the fraction is getting small, so the limit's going to be 0. So you can always expect that when the degree on top is strictly less than the degree on the bottom, you're going to get 0 as your limit. As long as it is a rational function, right? Just a polynomial divided by just a polynomial. Can't have anything else weird. You can't have any sines or cosines or exponentials or logarithms. Once you have anything that's not just x to an integer, a positive integer power or 0, then you're no longer a rational function. So be careful. Okay, last thing in this vein. What if we had the limit as x approaches infinity of, sure, 2x cubed minus 4x plus 1 over x squared plus 5. So now this is where you don't want to make the wrong choice. And let me see if I've designed this in a way so that it's terrible if we make the wrong choice. No, it's not that terrible, but it's terrible enough. So here's the wrong choice that you shouldn't write down. Bless you. So the wrong choice here is to divide everything by x to the third power. Because if you do that, you get the limit as x goes to infinity of 2x cubed divided by x cubed is 2. I should say dividing by x cubed. We get 2 minus 4 over x squared plus 1 over x cubed over 1 over x plus 5 over x cubed. And what happens is, and again, this is where I probably should have made it a little bit more challenging. Like I should have made it, I don't know, something else. But anyway, you're going to get 2 minus 0, which is 2, over 0 plus 0, which is 0. And although you could probably make a convincing argument here, it's not always going to be easy to tell if that denominator is slightly positive or slightly negative. We know from previous experience, I think, that when you get a not zero number divided by 0, your limit's going to be some sort of infinity, positive infinity or negative infinity. But it's really, really hard to tell this way because we don't actually know. Especially like if this had been a minus 5 here instead of a plus 5, this 1 over x minus 5 over x cubed, it's really unclear if this thing is slightly negative or slightly positive. This is the wrong way to go. The right way to go is to divide by the highest power of x that appears in the denominator. So if we divide by x squared instead, look how much easier this is going to be. We're going to have the limit as x goes to infinity of 2x cubed divided by x squared is 2x. 4x divided by x squared is 4 over x. 1 over x squared. And then the denominator, x squared over x squared is 1. 5 over x squared is 5 over x squared. And now we plug in and look what happens. We get 2 times infinity minus 0 plus 0 over 1 plus 0. And infinity divided by 1, I should say 2 times infinity divided by 1, is still positively infinitely large. So this is definitely going to positive infinity. So that means for this function, as you go to the right, it gets really, 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 really large forever and ever and ever. Well, let's look at what happens when you go to the left. So if we look at the limit as x goes to negative infinity of this same expression, 2x cubed minus 4x plus 1 over x squared plus 5. Well, we've already got the work written out right here. It's just going to be the limit as x goes to negative infinity of 2x minus 4 over x plus 1 over x squared divided by 1 plus 5 over x squared. And look what happens here. As x is getting negatively large, we get 2 times a big negative number minus 0 plus 0 over 1 plus 0. So in this case, we get a negative infinity as our result. Meaning this graph, as you go to the right, goes up, 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 and as you go to the left, goes down, 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 down. In fact, let's look at it because I do think it's worth looking at. I mean, I could probably say that's in general. Why are you not there? Fine, be that way. I think that's pretty much a generally true statement. The graph is usually worth looking at. It will usually tell you something. So here, if we look at y equal to, what was it? 2x cubed minus 4x plus 1 divided by x squared plus 5. Up, and then we zoom out. You can see, oh yeah, it gets really, really big, positively big to the right and negatively big to the left. So the graph is definitely in agreement with what's happening here. Kind of neat. No, let me say that. Okay. That is most of what there is to say as far as limits to infinity for rational functions, right? It's kind of one of these three cases. Either the degrees are the same and the limit's the fraction of the coefficients, or the degree on top is smaller and you get 0, or the degree on top is bigger and you get either positive or negative infinity. That's kind of the only things that can really happen. Okay. What else? Are we there yet? Just trying to think about if there's anything else I need to talk about before we start talking about continuity. Sure. Oh yeah. One more fun example. Sure. One more. Oh, question. Well, how about that? What a great question. Let's look at the limit as x approaches. Let's do negative infinity first of x plus 1 over the square root of 9x squared plus 1. Okay. So this is not a rational function. I want to make that really clear. It's not a polynomial divided by a polynomial because the denominator is not a polynomial. It's the square root of a polynomial, which is not a polynomial. So it's going to behave a little bit differently, but oftentimes we still kind of treat fractional things as rational-ish functions. Like they're still going to have some of the same behaviors. Now, here's a maybe tricky question. Here's an easy question. What's the degree on top? Yeah, show me on your fingers. It's this many. One. Okay. Now, this next question isn't really a valid question, but I'm going to ask anyway. What's kind of the degree on the bottom? This many, right? Because even though there's an x squared, it's in a square root. And the square root of x squared is kind of like x to the first, kind of. So we're thinking it's kind of like x to the first over x to the first. So it wouldn't be unreasonable to guess that the limit might be kind of like the quotient of the coefficients. The leading coefficient on the top is 1. The leading coefficient on the bottom is 3, right? Because it's the square root of 9. So we're guessing we might get something like 1/3. Well, we will eventually. But for this one, we won't. What do I mean? Well, let's take a look. So how do you even deal with this thing? There's a number of ways. I would say your best bet here is to factor out the x squared from inside the square root. That is usually the technique that we use. So I'm going to write this as the limit as x approaches negative infinity of x plus 1 divided by the square root of x squared times 9 plus 1 over x squared. So if I distributed it back through, I still have the same thing I had before. And then you can skip this next step if you want to. I like writing it just to make sure that everyone's on board. I get x plus 1 on top still. I'm just going to break up the square root of x squared times 9 plus 1 over x squared as the square root of x squared times the square root of 9 plus 1 over x squared. Same thing. So here's the things that are a little dicey. This is where it is absolutely imperative that we remember that the square root of x squared isn't just x, it's the absolute value of x. So here, I would probably just underline it and say absolute value of x, but fine, I'll show all my steps. So we still have the same limit, x on top. Square root of x squared is the absolute value of x, and we still have the square root of 9 plus 1 over x squared. Okay, now, important question. Is x positive or negative? It's the limit as x approaches what? What's x approaching? So is x positive or negative? Very negative, as negative as it gets. X couldn't be more negative if it's approaching negative infinity. So for this limit, we have to say that the absolute value of x is equal to negative x. So we're going to rewrite this as the limit as x approaches negative infinity of x plus 1 over negative x times the square root of 9 plus 1 over x squared. In case that is tripping you up, I'm going to go away from this for a second, but I'll come back to it, I promise. I'll remind you that 1, y equal to the absolute value of x looks like this. It is this v-shaped function, although I wouldn't write it like this. And I'll point out that over here on this side, you get y equal to x, and that's when x is positive. And over here, you have the line y equal to negative x, and that's when x happens to be negative. So when x is negative, the absolute value of x is really, really, really negative x. And then we just kind of apply the same techniques we've talked about before. I'm going to divide the top and bottom by the highest power of x, which is x to the first. I know it might seem like there's something else going on here. There isn't. So I'm going to rewrite this as the limit. Now this is where we need to be a little bit careful. I should say we should always be careful, but we'll be more careful here. X over x plus 1 over x. Now, when you're dividing things, division distributes across addition or subtraction. So that's why x plus 1 divided by x is really x divided by x plus 1 divided by x. But here, you don't get distribution because it's multiplication. So here, this negative x times the square root of 9 plus 1 over x squared is really, we're just going to divide the whole thing by an x. And we can't distribute that to each piece. Otherwise, you'd be dividing by x twice accidentally. So let's see, rewriting this, we get the limit as x goes to negative infinity of 1 plus 1 over x over the x divided by x is just 1, and you get negative square root of 9 plus 1 over x squared. Finally, we can actually take the limit. The 1 over x goes to 0. The 1 over x squared also goes to 0. And we're left with 1 over the negative square root of 9, or 1 over negative 3. Woof. Problems like this are kind of a pain in the butt. They just take a lot of steps. Now, I would certainly say you could have probably written less steps than I wrote, right? Like from this step, you could have just been like, yeah, that's the absolute value of x. You could have probably jumped straight from this step to that step. And then I don't know. I'm always writing too many steps probably for what the student would show, I think. Okay, what about the limit as x goes to positive infinity? Well, we're not going to show as much work because we don't need to. So I'll point out that if we take the limit as x goes to infinity of the same function, x plus 1 over the square root of 9x squared plus 1, all the steps are the same up until we get to right here, right? Up until there, we haven't done anything different. So I'm just going to skip ahead to there and say it's the limit as x goes to infinity of x plus 1 over the absolute value of x times the square root of 9 plus 1 over x squared. But now, since x is clearly positive, the absolute value of x is just equal to x. So the only thing that's going to change is we're not going to get a negative sign here. So we're going to get the limit as x goes to infinity of, let's just skip to like, sure, this step here, it's going to be 1 plus 1 over x over positive square root of 9 plus 1 over x squared, which means we're going to get positive 1/3 as our limit. So here's an example of a function that has a different horizontal asymptote to the right than it does to the left. And that is the most number of horizontal asymptotes any function can have, is 2 different ones. You can't have more than 2, right? Because the horizontal asymptote is really just asking the question, what is this function getting close to as x gets really, really big or really, really negatively big? And there's only 2 directions to go there, right? There's no other way you can go. Function can have any number of vertical asymptotes. It can only have at most 2 horizontal asymptotes. Just because I would want to see it, here's what it looks like. Oh, maybe not. Where's my cursor? Okay, there we go. Sure. Like the oldest man ever. Where's my cursor? Okay, so let's see. We had, what was it? X plus 1 divided by the square root of 9x squared plus 1. And let's zoom in a bit. So it's hard to really see that we actually have the vertical horizontal asymptotes we said we do. If you can't quite see them, draw them in. I know that one of them is y equals 1/3, and the other one is y equals negative 1/3. Oh yeah, now I can definitely see, yes, to the right, the function is getting closer and closer to 1/3, and to the left, closer and closer to negative 1/3. So if you're not sure if something's a horizontal or vertical asymptote and you're looking at Desmos, just graph them in there, and then you can be like, oh yeah, the function is, that is it, or it's not it. You should definitely be, have I not said you should be using that? You should definitely be using Desmos, right? It's a very, very useful tool to help you understand things. Okay. All right. Hopefully that was what you meant, Megan. Okay, cool. That's what I thought, but I just want to make sure. All right. What time is it? 2:05. Okay, cool. We should start talking about continuity. Question, yeah. Yes, there is. Thank you so much. Is there an attendance sheet? Yeah, good call. Ah, okay. So, just as a point of interest, since we've got this function graphed here, this function is continuous everywhere. This function, f of x equal to the absolute value of x, is continuous everywhere. I will mention when we talk about continuity, when you say a function is continuous, the everywhere is kind of implied. Right? Like if I say something's continuous, I mean it is continuous everywhere. On the other hand, I will point out, sure, why not? Let's look at f of x equal to 1 over x, which is your classic hyperbola. It's got this shape. It's got a vertical asymptote at 0. It's also got a horizontal asymptote at 0. And the language I would use here is that this function is discontinuous. What I really mean is there's at least one point of discontinuity. This function is actually continuous. Some people say this function is continuous. I don't love that language. This function is continuous on its domain, but it's not defined everywhere. It's not defined at 0. So f of x equal to 1 over x is continuous on its domain. Oh yeah, in the 19 series especially, there's like a terrible definition of continuity that I do not like. Fortunately, we're not in that class, so great. So f of x equals 1 over x is continuous on its domain, but specifically it is not continuous at 0 because it's not defined at 0. So not continuous everywhere. Specifically at 0. So I'll say again, when I say something is continuous, or usually in the 21 series, when someone says something is continuous, they mean it's continuous everywhere. And when we say something is discontinuous, it really just means it's probably discontinuous like at one point, or maybe a few points, but some finite number of points. This function is still continuous almost everywhere, just not at one place. Okay. So just so you're aware of what we sometimes mean when we say this. So, but let's back it up a little bit. So where am I here? Sorry, one second. I just want to make sure I'm doing the examples I intend to be doing, not you. There we go. Sure. So a lot of our continuous examples or discontinuous examples come from piecewise functions because they're the easiest things to make discontinuous easily. So here are a few examples. And I think I was actually using these before for something else, but they're still good examples. So let's look at this piecewise function. Yeah, we definitely talked about this one before, but it's a good example. Let's look at the function that is x squared when x is specifically less than 2 and x plus 2 when x is specifically greater than 2. Notably, you already know this function is discontinuous somewhere without even drawing anything because this function isn't even defined where? At 2, right? We didn't define it. We could define it at 2 if you wanted to, but we didn't. So this function, if we graph it, right, usual parabola shape to the left of 2. And usual straight line shape to the right of 2. And if you plugged in 2, you would get 4. So this hole here that's missing is the point 2 comma 4. And this function is discontinuous at x equal to 2 because f of 2 is not defined or does not exist. So one way to be discontinuous is just to not even exist at the particular point of interest. But sometimes you are defined. For example, can I fit you in? Yeah, I can fit. So let's say we had another example that was almost the same function, f of x equal to, now it's going to be x squared when x is less than or equal to 2. But instead of being x plus 2, it's going to be shifted up by 1. It's going to be x plus 3 when x is larger than 2. So similar graphical thing going on here. We're interested in what's happening at 2. And we see from the left, it's still the same usual parabola. everyone's favorite parabola. Maybe not. Maybe yours is my favorite parabola, the easiest one to draw. And then to the right of 2, we're going to have the line y equals x plus 3, which has the point 2 comma 5, or would if it was defined there. So it's looking like that. Clearly, you can look at that and see, oh yeah, it's discontinuous, right? If I tried to draw, and the way we said is, if you tried to draw it, you'd have to lift your pencil off the paper to draw it, or your chalk off the chalkboard. You'd have to like make a jump. This is a jump discontinuity, and this is discontinuous. Wow, can I spell? Maybe. At x equals 2, not because it's undefined there, right? Certainly f of 2 is defined. F of 2 is equal to 4, but the limit is problematic. The limit from the left, well, the limit as x approaches 2 from the left of f of x is the limit as x approaches 2 from the left of the left piece, which is going to be 4. But the limit as x approaches 2 from the right, well, we're going to use the piece where x is bigger than 2. And when x is bigger than 2, we get the function x plus 3. And if we look at that limit, as x is closer to 2, x plus 3 gets closer to 2 plus 3, which is 5. Those don't match. Limit doesn't exist. So your function can be discontinuous because the function doesn't exist. Or your function can be discontinuous because the limit doesn't exist. It can also be discontinuous even if both of those things exist. And they're not the same. For example, if we took, I could almost do this, sure, fine. I'll draw it again. I'm going to draw the same graph I drew the first time. Fine. Almost the same graph. Do I have numbers here? Am I just throwing in a random number for the sake of it? Yes, I am. Let's not just throw in random numbers. Let's change that 3 to an E. Sorry. And say our new function is pretty much the same as the first one, except we're now going to define that you get the function x squared when x is less than 2. You get the function 5x when x is equal to 2. Yes, I can. And you get the function x plus 2 when x is greater than 2. I will point out, I have made the middle piece annoying on purpose. I could have just said f of x is equal to 10 when x is equal to 2, right? Because the middle piece is only one single point. So it's kind of silly to define it this way, but that could happen. So just beware. Is that a hand, Megan, or just a, okay, cool. So this one, make my graph extra big here. So again, the same graph from the first graph where you have your usual parabola on the left. Ooh, okay, maybe. And your straight line on the right. But then at the point 2, the y value is actually 10. So this one is discontinuous because even though f of 2 exists, it's equal to 4. The limit is x. Sorry, f of 2 does not equal 4. What does f of 2 equal? 10. F of 2 is 10. Sorry about that. F of 2 is 10. And the limit as x approaches 2 of f of x is equal to 4. Because the limit from the right and the limit from the left are the same. But since the limit value and the function value aren't equal to each other, it's not continuous. So discontinuous because the limit as x approaches 2 of f of x is different than f of 2. All that to say, for a function to be continuous at a point, the limit value has to equal the function value. And implied in that is they both have to exist. So let me write a definition for you, and then I'll tell you what we actually do. Sorry, you might want to see that still. So definition. We say that the function f of x is continuous at x equal to a if the limit as x approaches a of f of x is equal to f evaluated at a. Now, included in all that is the fact that the function has to exist, the limit has to exist, and they have to be equal to each other. But saying they have to be equal to each other means they both have to exist in the first place. If they both don't exist, that doesn't mean it's continuous, right? Does not exist equaling, does not exist is not a recipe for continuity. Now, usually the way we check to see if something is continuous at a point is by checking all three things kind of in order. So, for example, if I want to determine whether f of x equal to, what do I got here? Sure. I don't love you. Okay, fine. F of x equal to, yeah, here's a fun one. Equal to 6 over x plus 2 plus e to the 5x. That's gnarly. When x is less than 0. And, sure, sine of 4x over x when x is greater than or equal to 0. That's a bad call. Let's put the equals there and not there. Good call, James. Yeah, okay. Sure. Whether this function is continuous at x equal to 0. Not really a question, but whatever. Okay. So, specifically, I'm going to ask another question with this after this, but right now we're just being asked, is this function continuous at 0? So let's go through the three-step process. The first step, does f of 0 exist? Which is why I needed to change where the equals part was, because otherwise it wasn't going to exist. Let's see. So in this case, f of 0, I'm going to plug the 0 into the top piece of the function and get 6 divided by 0 plus 2 plus e to the 5 times 0. That's going to be 6 divided by 2, which is 3, plus e to the 0, which is 1, which is 4. Cool, it exists. Now for the second part. And for a piecewise function, usually the second part means taking the one-sided limits. And usually, not always, but usually, one of those one-sided limits should kind of be using the piece you've already dealt with. So here, if we look at the limit as x approaches 0 from the left, let me write, does the limit as x approaches 0 of f of x exist? Well, left hand to right hand. For the left-hand limit, we're going to have the limit as x approaches 0 from the left of the piece where x is less than 0. So it's the same piece of the function we just used. And we're pretty confident that we're going to get the same value, right? Because if you're evaluating this limit, the first thing you're going to try to do is just plug in the 0 and get 6 divided by 2 plus e to the 0, which is going to be 4. But the question is, what about the other side? So what about the right side? Well, now the limit as x approaches 0 from the right, we have to use the piece where x is bigger than 0. And we have a sine of 4x over x. And as you might have noticed, we can't just plug in the 0. So what do? We use the techniques we talked about at the very beginning of class. We're going to rewrite this as the limit as x approaches 0 from the right of sine of 4x over blank times blank over x. And then we put in what we wish we had beneath sine of 4x, which is 4x. And 1 over there to balance it out. And then the limit of this part is 1 times, and this part the x's cancel, and 4 divided by 1 is just 4. Look, they're the same. How about that? So, yes, the limit exists. It's also equal to 4. So the limit as x approaches 0 of f of x is equal to 4. And then finally, thirdly, we can say that the function is continuous at x equal to 0. So f of x is continuous at x equal to 0 because f of 0 is equal to 4 is equal to the limit as x approaches 0 of f of x. Follow-up question. Where is this function continuous? which is a terrible question. I hate this question. I don't hate this question. I don't love phrasing it that way because really, when you ask this question, you should really be asking, where is this function not continuous? Because that's the easier question to think about. So let's see here. Where is this function f of x equal to 6 divided by x plus 2 plus e to the 5x when x is less than or equal to 0, and sine of 4x over x when x is greater than 0. Where is this function continuous? Well, we know it's continuous at 0. Where is the only other potential issue? Right. And the zero denominator, well, it wasn't a problem here because we already dealt with that. But there is a zero denominator potential issue right up there, right? If you set x plus 2 equal to 0, we see that x equal to -2, which is in this interval, is a place where this function is definitely going to not be continuous because it won't even be defined there. So we would say that f of x is not continuous at x equal to -2. And that's the only place. Because as I imagine, one of your teachers at least, that functions are typically a function is continuous on its domain. Meaning, and I'll say more about this in a minute, but basically any typical regular function you encounter in the world that's not some weird piecewise thing is continuous where it's defined. So this function, this top piece here, 6 over x plus 2, well, that's defined everywhere except for -2. E to the 5x is defined everywhere. And when you add functions together, their domains kind of overlap. So the only place that's a problem for either of these two things added together is -2. Down here, the only problem would have been 0, but we already checked 0. 0 is fine. So -2 is the only place where it's discontinuous. So we would say that f of x is continuous on the interval from -infinity to -2 union -2 to infinity. So generally, normal, and I'm putting this in quotes because what's normal? Normal functions are continuous on their domains or where they're defined. A short list. Polynomials. So again, this is non-negative integer powers of x. So something like f of x equal to something a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus all the way down to a sub 1 times x to the first plus a sub 0. Those are continuous everywhere because they are defined everywhere. I will also say, as we're saying this, polynomials are also differentiable everywhere, meaning their derivatives exist everywhere, even though we haven't talked about derivatives yet. Or you might say they're smooth, because although it's not a perfect way of describing differentiability, it is a pretty good way of describing if a function is differentiable, as if it's smooth, not pointy. So the absolute value function is not differentiable everywhere because it's pointy in one point. And then the next one on our list is typically rational functions. So polynomials divided by polynomials. I should have written p of x instead of f of x. Oh well. P of x divided by q of x. Those are continuous where they're defined on their domains. So as long as you're not dividing by 0, that function is defined there, so it's continuous there. If you are dividing by 0, that's where you've got a vertical asymptote typically. What else do we have? What else is in our list of typical functions? All the trig functions. Sine x and cosine x everywhere. So sine x and cosine x are continuous everywhere. The other 4 trig functions are continuous wherever they don't have a vertical asymptote. They're continuous. So tangent of x, cotangent of x, secant of x, and cosecant of x continuous on their domains. I mean, I guess I could be saying that for everything, right? Because sine x and cosine x, their domain is everything. So I could say, but I feel like it's better to say it's everywhere because then you're like, oh yeah, it's everywhere. What are the only functions I'm leaving out here? Oh yeah, exponential functions. So like e to the x, 2 to the x, 5 to the x, any positive number raised to the x power, continuous everywhere. And then the inverse function of those functions, the logarithmic functions, continuous on their domains. So, sure, I guess I could fit this in here. The natural log of x or log base 2 of x, etc., continuous on their domains, which specifically for those functions, when it's just x in the argument, is positive numbers. I think that's just about everything. There's a few functions we can make up still, but and then you can combine them together. So like if you add functions together or subtract functions or multiply functions, then they're continuous on the overlap of the domains. So the intersection of the domains. So for example, like if you had say the natural log, like for example, if your function was how much time? Yeah, sorry. I know, let me just try not to go too fast. If your function was, for example, say the natural log of x plus 3x minus 5 over x minus 7. Well, I know that the natural log function is continuous on its domain, and its domain is positive numbers. And this function here, this piece I'm adding here, we just can't have x equal to 7. So this function is continuous on its domain, which is all positive numbers except for 7. So f of x is continuous on the interval from 0 to 7, excluding 7, union 7 to infinity. Because it's a combination of typical functions, and we're just excluding the values of x that aren't in the domain. The real examples of discontinuity typically come from piecewise functions like we kind of saw already. So that's what you should, like when you're being asked about continuity or discontinuity, it's usually going to be like, is this wacky looking piecewise function continuous or discontinuous at this particular point? Yeah, trying to think. Oh, sure. And I guess I won't try to squeeze in one more example, even though I really want to. Okay, so next week we'll probably talk a little bit more about continuity, and I imagine you're getting into the limit definition of the derivative. So we will start talking about the limit definition of the derivative.